Find the coordinates of a point M in terms of a constant so that the points M and A at 0 at minus 1, 5 and B at 1, 2, 3 are collinear. Right, so for collinear points, when you're thinking in terms of vectors, you talk about 3 points and you can define different vectors between the points. So I could define AM or AB or BM. So if I can show that any two are scalar multiples of each other, that is enough to show that the 3 points are collinear. So let's say point M, if we say that M is at some unknown x, y, z, and we're looking to find those, it says in terms of a constant. So the constant often with vectors, with planes, it tends to be a t or a lambda or a mu, something like that. But it's something where it's a scalar, so you can multiply it by something, and basically it changes length and it can change direction if it's a negative. So if we say that M is at x, y, z, we already know where A is and we already know where B is. So if we can just consider the vectors AM and AB, if we know that they're collinear, then that must mean they're scalar multiples of each other. If the 3 points A, B and M are collinear, remember collinear means you can draw a straight line through all 3 points. But basically, if 3 points are collinear, then any 2 vectors involving those need to be parallel. For vectors to be parallel, one needs to be a scalar multiple of another. So this is not the only way you could write it, but I'm going to write AM is going to be equal to some multiple times AB, because they have to be parallel. So I'm going to call this T. You could call it K if you wanted to, but often for vectors you see T's as a parameter, certainly when you get to equations of lines. And when you get to equations of planes, you see lambdas and mu's quite a lot. Okay, so AM equals some multiple times AB. So if we just write AM in terms of vectors, so AM equals, remember we start at M, which is at x, y, z. That is the position vector of M. So this is OM that I've just written, minus the position vector of A, and A is at 0, minus 1, 5. 0, minus 1, 5. So AM is x minus 0 is just x, y minus 1 is y plus 1, and z minus 5 is z minus 5. So that is AM. AB equals, well, we're going to put B first as in the position vector of B, OB, which is 1, 2, 3. So then we're going to end at B and start at A, because you're going from A to B. 0, minus 1, 5. So AB is going to be 1 minus 0 is 1, 2 minus 1 is 3, and 3 minus 5 is minus 2. Okay, so we have said that AM is some multiple, scalar multiple T times AB. So let's just write that down. AM, x, y plus 1, z minus 5. Equals T times AB. AB is 1, 3 minus 2. So that means x, y plus 1, z minus 5 must equal, if we're multiplying by a scalar, we literally just times all of these by the scalar. So that is t, 3t minus 2t. And remember, we're looking for the coordinates of M in terms of the constant. The constant that we chose was t. So really we want OM, the position vector of M. So we want the x, the y and the z. So that must mean x, y, z equals, well, x we know is just t. We know that y plus 1 is 3t, so y must be 3t minus 1. And z minus 5 is minus 2t, so z must be minus 2t plus 5, which is the same as 5 minus 2t. Okay, so that is the position vector of M, which is OM. So the coordinates of M in terms of the constant being t, are t, 3t minus 1, 5 minus 2t. For a lot of problems involving collinearity, you just have to show that 3 points are collinear, and then you just take them both and show that one vector is a scalar multiple of the other. In this case, we were kind of going backwards. You're told that they're collinear, and you need to work from there. So it's a bit more complicated, a bit more algebra, but that's the basic concept. Okay, you've got 3 points on a line. If they're collinear, then clearly vectors along that line need to be parallel. If they weren't, then how could it possibly be collinear?